Hi everybody, so welcome back to another chat where we're going to talk about another important aspect that you'll be going through during your PhD with the ATLAS experiment. You've already done some Monte Carlo generation where you've generated the events, and I talked a little bit about the different levels of simulation and reconstruction, and you had done a little bit of analysis to take those objects and try to reconstruct, for example, the Z-prime mass. In the real analysis that you'll perform, you have to apply that selection to objects which have been reconstructed by the ATLAS detector. When we talk today about the event selection, this is the idea of running a series of selective cuts over either real data that's been fully reconstructed or your Monte Carlo backgrounds to the search you're doing, and even the Monte Carlo signal as well. So when you start to look at real data, there are more cuts that you have to take into account or consider to really try to pick out your signal above the background, and also make sure that data agrees well in the regions where you expect it to. So as I say, today we'll be going through what we call the event selection, and on the left hand side, so this will depend very much on the analysis that you're actually considering, but if you look on the left hand side here, you can see a general list of criteria or cuts that we consider when we're performing an analysis. So we start at the top here with the trigger, and I'll go through each of these cuts one by one and kind of explain their motivation and why they're an important aspect of any analysis that you do. So starting right from the very beginning, we know, for example, from what you've looked at so far, that there are around 40 million collisions per second at the LHC. We have a bunch spacing of only a few, maybe up to 9 nanoseconds between the bunches of protons colliding. And the reality is that you just can't write 40 million events per second to disk. There's no fast enough computing. The heads of the hard drives can't write themselves fast enough. So I think we've already introduced this concept of a trigger, the idea that we, at the hardware level, very quickly decide which events we want to keep and which that we just don't record. And if we don't record them, then they're gone forever. And so we can write to disk at about a rate of 1 kilohertz. We're trying to improve that with time. So 1,000 events per second can be written to hard disk and then analyzed later. And so this trigger menu per se, or all of the triggers that ATLAS has collectively described, that within that 1,000 events per second, we want to write 200 events that have jets with a certain energy in it, 200 events with leptons of a certain energy, some with missing energy, and so forth. And you can imagine that 1,000 events per second is essentially a bandwidth that we can fill with this menu of all the different kind of physics we want. And I'm going to talk a bit more about this in detail. But because any specific analysis you do is not going to want to look at all of the different kinds of new physics, you might be only interested in that amount of physics that we've recorded that has 1 lepton in it, or 2 leptons, or maybe 3 jets, for example. And the trigger is a way that you go down from all of that data that we've collected just to the subset that your analysis is interested in. So of all the triggers which are run when we're collecting the data, with your analysis, as we say, offline, after the data's been recorded, you can request that you only look at the events which have passed a certain trigger. So let's follow this green arrow over here to this diagram in the top right. And I'll just talk a little bit about the trigger and how what it actually looks like when you require something. So I've got here 3 different colors, 3 different names of triggers. One is called EM20, one is called EM50, and one is called 2EM12. So there are these names for triggers in the ATLAS experiment that essentially you will learn how to decode, but I can already tell you that this one says that there has to be at least 20 GeV in the electromagnetic calorimeter. This trigger is requiring that in the event there was at least 1 cluster of EM energy with at least 50 GeV of energy. And this last trigger here is requiring there are 2 clusters, each of them have 12 GeV of energy. So if you were looking at, for example, an analysis that cared about having 2 electrons in the event, you could ask for the 2EM12 trigger, and that would select all of the events that had 2 energy deposits of at least 12 GeV, and that would likely select all of the events that you were interested in for your electron analysis. If you're doing a jet analysis, then these triggers wouldn't be very useful to you because it doesn't tell you if there are jets in the event or not, just that they're electromagnetic deposits. Similarly, you can notice that these energy thresholds are different, or you ask for a different number of these thresholds, because if you think about this EM20 trigger, right, it's a very low energy, and because of the number of collisions we're doing, you can imagine there's more events with low energy, and as you see those generally falling distributions, because of the rarer head-on-head collisions, you get fewer and fewer events with higher energy. So if this threshold is too low, let's say you had EM10 instead of EM20, then you would just have too many events being recorded. That bandwidth of 1,000 events could be filled up just by this one trigger. So you have to set the threshold such that every trigger is only taking its fair amount of that bandwidth. So these generally have been decided that, for example, so you have EM20, some people may be interested in just higher energy information, so they choose EM50. Some people might want lower energy stuff, but because you want that lower PT threshold, you require that there are 2 deposits of that energy. So 2 EM12, even though it's a lower threshold, because you're asking for all the events that have 2 of those deposits of energy of 12 GeV, then it's not taking up that much more of the bandwidth, right? Even though it's lower PT, because there are fewer events that have 2 of those deposits in it. So this is a very finely structured list of trigger menus that's always discussed among all of the physics groups, and that you can select what you want. Another thing that's important is what we call the trigger efficiency turn-on curves. So if you see this plot here in the top right, I've got efficiency, so the rate of accepting real events that goes from 1, so 100% acceptance, down to 0. And on the x-axis here, I've got the true PT of your object. So here, let's just take electrons as an example. So if I asked for the EM20 trigger, then you can see from the true PT of my electron, for example, that as you get to around 20 GeV, you can see that this efficiency, anything below 20 GeV, wouldn't register, it doesn't pass that trigger, so we wouldn't select that event. And if we're at very high energy, say above 50 GeV, then you can see this EM20 trigger selects almost 100% of those events that have at least 1 lepton with 50 GeV in it. However, even though we're asking for an EM20 trigger, you can see that around 20 GeV, it may only have, and this is just a random example, 50% efficiency. So even though we've asked for 20 GeV, it's not actually selecting all of the events with 20 GeV until it gets to maybe 30 GeV. And this is due to resolution and other noise effects and uncertainties that mean that you don't always get exactly at that threshold. But we'll come back to how you fix that later. And similarly for EM50, then you have its own turn-on curve. It may be steeper or less steep depending on the energy or the number of objects you're looking for. But you've got this idea of this turn-on curve, and what you're interested in is really the region when you get to 100% efficiency. So we'll come back to that in a little while. But this is the idea of the trigger that you'll be requesting. And in these different columns here, you can see that I've got all of the selection we're going to make, and then I've got in the first column data, in the second column all of your Monte Carlo backgrounds that you might be considering, and in the third column your signal, let's say Z prime for example. And for the signal on the Monte Carlo, well, most of the events you'll be generating have at least 1 lepton in them if we take the 1 lepton case. So by default, especially if you've got some filter on that sample, it's going to be very efficient at passing this cut. However, as I said, the data has everything in it. So when you apply this trigger selection, you're automatically probably cutting down the amount of data by a factor of 100. So you're only looking at that important part that you're interested in. Next we come to the event quality. So this is, again, mainly applicable to the data. The idea that the detector is not working completely nominally at all times that we're collecting data. Maybe the magnet had to be switched off temporarily for some reason, or there's more than expected noise in the calorimeter, and if you're looking for electrons, that's a problem. Similarly, if you're worried about tracking, and then there's maybe a problem with the silicon tracker at the moment, then that may have been switched off for a certain run or a certain period during a run. And if you've heard of something called the good runs list, then this is a list that for every run at the LHC, for every time we ramp up protons, collide them together and start collecting data, for every luminosity block, which is roughly a few minutes in length, there are flags for every detector system that tells you whether it's working nominally or not. And so when you're looking at an analysis, say for 2 electrons, you say, I care about the tracker, I care about the electromagnetic calorimeter, I don't necessarily care about the muon spectrometer, and that will require that in that good runs list, it's nominally marked the inner tracker and the electromagnetic calorimeter as working nominally at that time. If they are marked as not working, then those events are excluded by this cut. Whereas if you're doing a dielectron analysis and it says that the muon spectrometer wasn't working, then you don't necessarily care that it was switched off because you're just looking at electrons. Right? So again, dependent on exactly what you're looking at, this kind of event quality can tell you if the detector's working nominally, if there was noise in the calorimeter or some other expected event, so that you make sure that you're getting the best quality of those recorded events. And again, for the data, you'll have some efficiency loss. Hopefully it's very small, maybe only 5% of the remaining data. But for the background and the signal, which is Monte Carlo, we generate our Monte Carlo in ideal conditions. So there should be no loss from this cut in the Monte Carlo. Okay, so moving next on to the PT cut, or the energy or ET cut that you would apply. So generally you go through all of the objects that you're interested in. Again, if we stick with the electron analysis analogy, you go through all of the electrons in the event and ask them to pass some threshold. So if we'd used our EM20 trigger, then we may ask for the leptons to at least have an energy of 30 GeV for every electron in the event. Okay? And why do we do this? Well, if we come back over to our trigger efficiency plot, then we can see that even though we asked for the EM20 trigger, it's not fully efficient by 20 GeV. And the difficulty is that in Monte Carlo and data, this turn-on curve can be slightly different. And you can account for scale factors that reweight the Monte Carlo to match the data better. But because it's such a steep curve, you can get some mismatches. And one of the easier things to do is to request a PT after you've selected them with your EM20 trigger. You ask that all of your leptons pass a more stringent PT cut so that you know you're only selecting events that are in this plateau region where you know the trigger is working 100% nominally. So this is an easy cut to make that just removes a lot of the complications. It may end up removing still a bit of your data, but hopefully not the data you're really interested in. Similarly, it may be advantage of getting rid of some of the low energy background, whereas if your signal is very high mass, you know, if you have a 1 TeV Z prime decaying into 2 electrons of 500 GeV, then it doesn't really make a difference if you apply a PT cut of 30 GeV. You're not going to lose that much of your signal. So it's a cut you can make without worrying about destroying your signal. Okay, and then lastly on this, I'll just come to the eta requirement. So remember, eta is this logarithmic based angular variable. In fact, I drew a diagram here of the Atlas detector. Again, forgive my drawing, but you can see the kind of barrel shape of the detector. And along with this barrel shape, and I've coloured in for some of the inner detector, the electromagnetic calorimeter and the hadronic calorimeter, and then the muon spectrometer would be outside of this. But I drew on this eta pointer as well, so eta of 0 would be pointing directly up. If you go exactly down the beam line in one direction, it would be an eta of infinity, in the other direction an eta of minus infinity, and you can see that I've drawn this special value of around an eta of 2.5. So the reason that I've done that is that we usually require that, especially for most of our lepton analyses, that the eta is, and the absolute eta, because it can be positive or negative, is is less than 2.5. So it's in the region of around 2.5. Now, why do we do that? So the main reason, especially when you're doing lepton searches, is that the inner detector, which is the precision tracker for our experiment, is very important at getting the PT right and making sure you don't have fake leptons, such that we want to restrict ourselves to only this precision region. And also the calorimetry is particularly finely segmented in this more central region of the detector. It includes a little bit of the end cap as well, but you can see the structure of the end cap, because more hadronic activity ends up going down this way. You have the forward calorimeters and then more hadronic calorimeters, and we don't have so much electromagnetic calorimeters there, but we do have some, so we allow this eta region up to 2.5. We could include even higher etas, so this very forward region. That's something that some specific analyses can look at. But for a leptonic analysis, the problem is that the more forward you go, if you imagine your proton collisions that aren't head-on that create your Z prime necessarily that decays into the detector, but maybe you have glancing blows and a lot of hadronic activity, that will tend to be more forward in the detector. It will tend to go in the direction of the beamline. And so the amount of background you get in these regions is much higher, whereas your signal is tending not to go in that direction. So we tend to make a cut to limit ourselves to the more precise region of the detector and where most of the signal is going to go anyway, so that when we make this cut, we're not getting rid of much of the data, background or signal, but we know that later we're restricting ourselves to a region that is particularly interesting for the search. We're not losing much by going to this region. I mean, this could be even higher, like 0.98 for most of these, right? So you're losing only a couple of percent in most of these analyses. Okay, so far all of the cuts that we've described, and sorry, I should mention that for each lepton you require that they are within this region. So if an electron was here, it would only be accepted if it's in this region of the detector. If it's got larger than an eta of 2.5, then we don't regard that electron in the analysis. But depending on the analysis you're doing, this eta range might change. It depends on which parts of the detector essentially you're including. So everything we've talked about so far we call the acceptance cuts. It's basically like choosing a region to look at in the analysis, but it's not particularly picking out your signal versus your background. It's just setting the phase space of physics that you're going to be looking at. The cuts that we're now going to come on to are called the efficiency cuts. So you might have heard someone ask, oh, what's the acceptance times efficiency of your analysis? Well, when they say acceptance, they mean these cuts. And when they mean efficiency cuts, these are the cuts now that we're particularly using to differentiate our signal from our background. Okay, and so in this bottom diagram here, the main idea is you can imagine if you don't have very good differentiation between your signal and your background, here again we have, let's say I had two muons or two electrons, and I reconstructed their invariant mass to find what the mass of the object they decayed from. You know, we might have my Z peak here around 90 GeV. This is number of events on the y-axis versus the mass on the x-axis. And you can imagine, let's say I'm looking for a signal around 1 tera electron volt, my Z prime decaying to 2 leptons. And you can imagine if I don't have very good signal to background differentiation, maybe my background would follow this red line, this red dash line, and so I wouldn't really be able to see my signal very clearly. And the idea of these efficiency cuts is a way to reduce the so-called reducible background, the parts of the other processes of physics which we can discount, while retaining our signal efficiency. So if you can push this red dash line down to the black line, the background, which may at some point become irreducible, there's no way to get it down any lower, would be here, and then your signal is very clear over that background. So it would mean that when you're doing this search, you would have a much higher signal significance when you're looking for that signal. So all of these cuts we're talking about now are trying to beat down that background while retaining our signal. There's no point if you're getting rid of the background and you also kill the signal as well. We want to get rid of the background while retaining as much of the signal as possible to get a better signal to background ratio. So the first general cut that I'll talk about is a very broad category. This is probably the most important in all of the selections that we'll talk about today. And I've generically called it here object selection because it will depend very much on the object that you're looking at, right? So if, as I've been going in the lepton way, if you talk about electron identification, this is trying to make sure that you're identifying electrons as opposed to jets, which might fake an electron. We'll talk about that in a second. But you may equally be looking for top quarks, and so out of all of the jets you see at the LHC, how do you know which ones are jets coming from a top quark? Or maybe you're looking for decays that have B quarks in them, so we have something called B tagging, essentially identifying the jets that come from B hadrons. So this object selection depends very much on what you're interested in, but I'm just going to give you an example now of talking about the electron selection, for example. So for the electron selection, if we go over to the left-hand side here, to me, right-hand side to you, you can see again, kind of looking down the barrel of the Atlas detector, you can see this kind of schematic. So in the center we have the tracking, then we have the electromagnetic calorimeter, the hadronic calorimeter, and then the muon spectrometer on the outside. And so what I'm showing here is that generally if we think of electrons, we think of a track in the inner detector, and then it showers in the electromagnetic calorimeter containing its energy so that we can tell how much energy it had, and that's our electron. And if we think of hadronic activity, say a proton or maybe a pion decaying, we think of the track going through the inner detector, mostly into the electromagnetic calorimeter. Maybe it starts to shower, but most of its energy is going to be deposited in the hadronic calorimeter, again containing its energy. Why does it punch through further? Well, because it's a hadron, it has more momentum, more massive particles, so it makes it deeper into the experiment. And it's also interacting via the strong force rather than mainly electromagnetically, and the detector is designed in that such a way. So this is the normal picture. And it's kind of that base level that you first learned when you think about the Atlas detector and particle identification. But in reality, of course, with all things, it's much more complex than that. And so if you think of your friend the electron here, but we're starting to think about these highest electron energies ever seen, then rather than just be well contained within the electromagnetic calorimeter, which we hope they still mostly are, you could imagine you could get such a high energy electron that it starts to punch through, and we literally call it punch through, into the hadronic calorimeter. And you can see when it starts to do that, well then, our electron may start to look like a hadronic jet. And equally, you can imagine our hadronic jet. Maybe there are certain cases where that jet, even though it's got higher momentum, maybe it has less energy, so it starts to slow down and shower earlier in the detector and leaves a smaller deposit in the hadronic calorimeter and a bigger deposit in the ecal. So you can see in these cases what we call an electron and what we call a hadronic jet starts to become a bit more muddled. Okay? And so this is where, for electrons specifically, the world of electron identification comes in. And we can look at these shower shapes and the tracks, and we can use that information to try and differentiate better what we really think is an electron and what we really think is a jet. So just to take some of those variables, for example, and I say when I started the Atlas experiment, we literally came up with some variables and made some cuts by hand. Luckily, things have got much more clever recently. Within the last 7 years or so, we've been using an electron likelihood. So basically, we had a boosted decision tree and then a likelihood approach where we put these variables in, and then it optimizes for the real electrons versus fake electrons, and the algorithm decides where the best cuts should be placed. And in that way, where as humans we might have placed a cut on one variable and another cut on another, this code would be able to say, well, actually you should only cut on that variable because once you've made that cut, this other variable isn't that sensitive anymore. Whereas we might have made that cut twice and then hit our signal efficiency twice for no gain in background. So the likelihood is a much better approach. And the way it's certainly going now for things like top identification or tau identification is obviously this new world of using neural networks. So using a recursive neural network to pick out tau, hadronically decaying taus as opposed to other hadronic activity is currently keeping the same signal acceptance and a factor of 10 reduction in background. So those huge improvements that these techniques can bring. but what are the variables that we can actually use to try and differentiate between these? So there's really a long list of 20 or so of these variables, but I just pick out a few that you can quite easily imagine. So one we literally call hadronic leakage. It looks at the amount of energy in the hadronic calorimeter versus the amount of energy in the electromagnetic calorimeter. And as you can imagine, for hadronic activity, you would expect this ratio to be larger, more energy in the hadronic calorimeter, less in the ecal. Even though you can see there's overlap cases, we're not just deciding on this one variable, but it's one that helps us get towards that answer. So this ratio is still very useful. Another one is simply the shower width. You can see from the decay that, due to random processes, this energy tends to spread out through the Compton scattering and pair production and other processes. And there will be differences in the shower width. Maybe an electromagnetic jet will be more collimated, whereas a hadronic jet will tend to spread out more, perhaps. And that can also help you differentiate between your jets. And then again, we can go into even more finer detail. There's a variable called like E21. So within the electromagnetic calorimeter, there are actually numerous layers. I think more than 3 layers and a pre-layer of the calorimeter, and you can measure the amount of energy deposited not just in total, but in each layer of the calorimeter. So, if it's an electromagnetic process, then perhaps it will dump its energy quicker into the electromagnetic calorimeter, so you would expect to see more of that energy up front, and then the momentum's very quickly stopped, and so you have less energy in the later layers when that shower begins. Whereas for hadronic activity, again, because it has more momentum, it could tend to deposit some energy more evenly, or more throughout the calorimeters, and so this ratio would slightly change. And again, no one of these variables is really a smoking gun, but once you have all of them, it starts to make the picture much more clear of if you have something that's more likely to be an electron or more likely to be a jet. And so, in fact, we don't just have one selection and say, okay, this is our cut. Analyzers are actually given the ability, you will often hear of working points. And so for the electron identification, for example, you'll hear of a loose, medium, and a tight working point. The looser selection is erring on the side of caution, in as much as it is accepting the maximum amount of electrons possible. It's very loose in its requirements, which is great if you want to accept as much as possible, but because those cuts are looser, it lets in more background. Whereas tight at the other end of the spectrum is extremely harsh. For the same energy of electron, you might, instead of accepting 90% of those real electrons, you might only accept 80 or 70% of those electrons. But the advantage is that you can suppress the background, the fakes, much more strongly. So depending on the analysis you do, you can care about one of these versus the other. And then, as you can imagine, the medium works point, just like Goldilocks, is just in the middle. It's not too loose and it's not too tight, so many analyses end up going with this. Okay, so that's talking to you about the object selection. Again, for the B-tagging working points, there you'll hear things like 88% working point, 75% working point. Those generally mean the amount of true B-tags that they accept, or they're aiming to accept. Similarly, with the top tagging, you'll hear something similar as well. We're going to carry on now to talking about our isolation cut. So again, this is another selection which can help you in trying to pick out your signal versus your background. And so I bring you down to this diagram here, kind of in the middle. And you may have not come across this before, but if I talk about a cone of a certain delta R size, delta R is defined as the square of the eta plus the square of the phi, or the differences of those, and then all square rooted. And so from this you can define an opening angle of a cone, as I've drawn here, and we can use this, and in fact 2 definitions there, to define the isolation of an object. So imagine that this is an electron with inside your calorimeter going through the inner detector, and the track is pointing in a certain direction, or the centroid of your deposit, and I can draw a cone around that, as I've drawn here in green, and then with a certain large opening angle, I can draw another cone around this, or within the vicinity around that energy deposit. Now, you can think that if your electron is very well contained, has a very narrow shower of particles, then the amount of energy that makes up that electron will almost completely be contained within this certain shower. And in fact, the way we define these cones for isolation are usually PT dependent. So the higher the energy of the electron, the larger this cone gets, because you expect the shower to spread out more. Whereas if there is more energy in the outer part here, it can mean a number of things. So if I take you to this diagram on the left, what you don't want is to have kind of double counting of energy in your electrons, or you may not want your, if it's in a very busy final state with lots of jets and so forth, you don't want those energy calculations to be disrupted by each other. So one example, the ideal world is you have your electron in the inner detector showering in the electromagnetic calorimeter, and then you're done, you've got your electron. But imagine, first of all, that you have two electrons that are very close to each other. Well, as they shower in the electromagnetic calorimeter, you can imagine the showers start to overlap with each other, and that can cause you problems. Now, these days there are some clever algorithms sometimes that are able to then, especially for jets, separate which energy belongs to which jet and which belongs to the other. But you can imagine in terms of isolation, in this case, where they're close together, you would start to see more energy in this outer cone than you would if the electron was well isolated or on its own. So there are analyses that can make cuts that say that only if the fraction of the energy in this outer cone is large compared to the energy in the inner cone, then you say the electron is poorly isolated and you want to reject it. You want to reject the cases where it's close to another object, either electron or maybe even sometimes too close to a jet. You can actually sometimes just do a delta R cut between any electron and jet in the event you say they have to have a minimal separation to be accepted. But isolation is another way to do that, and it partially also helps you differentiate, because electrons in the electromagnetic calorimeter will be generally more collimated, so it also partially helps you differentiate between jets and electrons as well. Although it's mainly for this kind of making sure you're not close to other objects. And again, if the calorimeter is a bit noisy, then again it makes sure that you're not near a hot region of the detector, which is then maybe putting off your measurement of the electron. So it's just another one of those cuts that can be used. And again, for your signal, it should hardly affect it. These should be very good quality electrons, so over 95% of them being accepted. And similarly, for most of the data and background by this point, you should be okay that you're not getting rid of too many of those. But it's something that can just stop you running into problems later, essentially. That you find an event that's very high energy then and you get excited, but if you look at it, you see, oh, actually it's a very busy event and this electron might have had its energy miscalculated or something like this. Okay, so as I've been talking, I haven't got to the opposite charge or the mass cut yet, but again, for each of this object selection and isolation cut, in the case of electrons, for every electron in the event, you request that it passes your object selection and it passes your isolation. What you're doing for every event, so we have a collision at the LHC, we've decided that we want it because of the trigger, we've decided the event quality is good, now we're interested in electrons, we say how many of the electrons in the event pass this PT cut? Let's say we had 3 electrons in the event, okay? Let's say we had 5 electrons in the event. We ask the PT cut, do each of these electrons have greater than 30 GeV? Oh, one only has 10 GeV. Well, we reject the electron, but we still keep the event, but we only consider these 4 electrons in the event. Then I say, are all these electrons within an ITER of 2.5? Yes, they all are. Okay, we carry on. Do all of these objects pass the electron object selection at the medium working point? Okay, one of them fails the medium working point. Maybe it was actually a jet that was just faking electron. So now we've got 3 electrons left. Now let's say, just for argument's sake, that the isolation cut, none of them pass the isolation cut. Okay, so in that case, I've got no electrons left in the event. I'm only interested in this analysis in electrons. Therefore, I throw the event away. I go to the next event in my collection and I do the whole process again. And I keep on doing that, but now let's say I've got down to a point where I had 3 electrons in the event after the object selection. Let's say they all pass the isolation criteria. Okay, we come on to the next cut now. So here we're talking about the opposite sign charge. So this isn't always implemented, but it can be very helpful. If I take you down to the diagram at the bottom right here, one thing with the strong magnetic field, the few Tesla field, which is put over the Atlas detector, you can see that depending on the charge of the particle, it will bend in a different direction. So for example, a muon will bend in one direction, whereas an anti-muon will bend in the other direction. Similarly, even though it's harder to see exactly, for an electron or a positron, before they shower, they will bend in slightly different directions. Now, if you're looking at something like a jet, then a jet, because if it has, it's hadronizing many pions, pluses and minuses and so forth, you don't really see a clean charge, you'll just see this shower of particles. You can imagine that for jets, it's essentially random whether you would accurately measure a plus or a minus to the charge. So it's random for that process. Whereas if you're looking for something like a Z prime or a graviton decaying to 2 leptons, well, you know because of charge conservation that that electron should be, a plus and a minus. So you can require that the leptons that you select have opposite charge, and that will cut down by a factor of 2 the random charges that you would get from any jets that have continued to even pass your object selection to that point. So it can be a way of cutting down your background even further. For many searchers, the QCD background isn't a dominant background, but it's still something that could be useful. The problem that you have, and we haven't even gone into uncertainties yet, that's for another talk, another time, but you can imagine for muons, because they go all the way from the inner detector into the muon spectrometer, there's a very big lever arm over which that magnetic field can bend the path of the muons. Even for the highest PT muons, which look very straight, it's enough of a curvature that you can tell essentially whether it's a mu plus or a mu minus, which is great. But you can imagine for electrons, because that's happening all in the inner detector, it's not as easy always to tell the charge. And we have something called charge mis-ID, essentially the misidentification of the charge. So you have to take into account when you're using this cut that you will accidentally remove some real electrons as well if you require that there are 2 electrons in the event with opposite charge. So going back to this point where we got to an event that has 3 electrons left up to this point in the event selection, now I've got 3, well, I could choose the combination of these leptons that have opposite charge, right? So maybe 2 have a positive charge, 1 has a negative charge. I could then say, okay, I'm going to match, this negatively charged electron with either of these positively charged electrons to form a pair, because I'm looking for a pair of leptons, a pair of electrons for my Z prime decaying. How do I choose the difference of between those 2 positrons at this point? Well, usually because we're doing a high mass search, you look at both combinations and you decide which has the highest mass pair, and then you choose the 2 oppositely charged leptons that give you the highest mass, and that passes on to the next stage. If you're lucky, you only have 2 leptons left anyway, and then you can be done. And if you're doing something like a W prime search, for example, and you only want 1 lepton in the event, you might actually choose that if you end up with 3 leptons, you reject that event. Because if you're looking for events that only have 1 lepton in it, right, then if you have more, then there are more processes in physics that could provide that and may again be a background to you. So you may only want to have 1 good lepton at the event in the end. The same could go when you have 2 leptons. If you're looking for 2 leptons and you have 3 at the end, then you could reject any of those events. But it depends on your analysis of whether it's an advantage looking at the combinatorics and taking the best ones left, or only taking events that have exactly the number of leptons you're looking for. So that's something that every analysis has to study. So when I finally found my pair of leptons that I like in this event, then I form the invariant mass between them, and I can make some minimum cut on the mass. Generally, you choose a mass cut that's at least twice the PT cut. So here I could choose a mass cut of greater than 60 GeV, for example. This is just to ensure that, again, we're mainly interested in high mass stuff, so it's fine. But you can have, if you had those 3 leptons left, maybe you chose one that's not really a real electron still, or is very low energy lepton. When you form, well, sorry, not, it has to be at least 30 GeV, but when you put them together, maybe because of the angle, they give you a very low mass, for example, so you don't care about those events. I mean, here we're talking about really just cutting off this low mass region where we don't really care about anyway, but it's something that's just done, you know, the background could be higher in this low mass region as well, so it's just easier to make a clean cutoff, essentially, and then consider this region above. Okay, so now we've gone through essentially the whole of the event selection or the reasoning behind these kind of cuts that you'll make. Again, you may see more, or you know, some intricacies in some of the specific analyses that you'll be performing. Mainly, this kind of covers the broad bases of everything that you'll be dealing with in the ATLAS experiment. So good luck, have fun, and hopefully you find some new physics. Okay, I'll speak to you in the next one. Bye-bye.